Good morning, Astronomy 1020. Welcome to our 11th lecture. This week, we take a break from learning about stars, and we talk about one of my pet subjects, one of my favorite subjects in all of astronomy/physics. That's Albert Einstein's theory of relativity. We'll be covering special relativity a whole lot, and a little bit of general relativity. Ironically, it's the general relativity that we really need for this course. Because as we start to watch stars go through subsequent levels of nuclear fusion, run out of that fusion, and then gravitationally collapse, sometimes explode, and sometimes collapse forever, the normal laws of physics, the old laws of physics, begin to break down when you compact crazy amounts of matter into smaller and smaller volumes of space. We need a new, more extreme theory of gravity to deal with those things. That theory of gravity, our top level theory of gravity today, is Einstein's theory of general relativity. General relativity is insanely complex. To really get a full understanding of it, you kind of need to start with the gateway drug of special relativity. So we're going to start with our gateway drug. I'm going to bring you guys, behind the playground. I'm going to get you hooked on special relativity. And then when I give you GR, that's it. Your life's over. It's never going to be the same again. So come hang out with me.
Been waiting for the whole semester for my life to end.
All right. All right. Maybe I shouldn't be making those jokes. Times are morbid as they are. Okay. So let's get right into it. I'm going to give you a little bit of historical background about relativity, but ultimately, whether you're dealing with special relativity or general relativity, why does the slideshow not work? Okay, we're going to be dealing with a new theory of physics that requires us to think in multiple dimensions. And it occurs to me that some of you may not have a firm grasp on what a dimension is. Let's test that theory. Can anyone out there explain to me what a dimension is? Like, what's the difference between 2D and 3D, 1D and 4D?
It's to put it in simple terms, it's the number of perpendicular axes that you can use.
Yes. Vladimir, I know you're intending to be a mathematics student. Because there are many different ways to construct coordinate systems, you guys in your grade school are most kind of familiar with the Cartesian coordinate system, which is X and Y perpendicular to each other. And as we get more advanced and sophisticated in our mathematics, there are other types of coordinate systems that we can deal with, like, for instance, spherical coordinates. Or you guys might have learned polar coordinates when you were in grade, even if you took a simple math class. I bet at some point you had to see polar coordinates. Why am I in caps lock? And that's a two-dimensional coordinate system that uses sort of a radius and an angle. The three-dimensional version of polar coordinates are, of course.
Oh, by the way, I remember you mentioning 4 pi radiating sphere. I was like, what the hell is he talking about? So I ended up Googling it. So that's the version of unit circle.
The unit circle works in angles 0 to 360 degrees, but in three-dimensional space, 360 degrees is not sufficient to explain a sphere. For that, you require knowledge of
cones,
spherical geometry or spherical trigonometry. The unit of angle when you use cones is called a stradian. That's a little bit over this class's pay grade, but since you're a math student, you should know, you eventually are going to have to learn about this. Spherical geometry is a big part of astronomy, so I don't feel too bad talking about it a little. Anyways, my original point was perpendicular is one way to look at it. There's a fancy mathematical term for perpendicular. It's called orthogonal. It's cool to bust out a couple of fancy sounding vocab words. Orthogonal means perpendicular, but it doesn't necessarily have to be X and Y. That's all I'm going to say about that. Let's talk about dimensions for a second, because eventually we're going to come up with a four-dimensional theory of space-time. That's right, we're going to talk about space-time. Woo! Okay, so I thought it might be good just to talk about some basic stuff first. And one of my basic starting points of this lecture, I don't want to do too much time on it. By the way, I'm getting all kinds of wacky focus issues, so we got to open up that Logitech. Forgive me if the audio cuts out here. Let's
That
talk.
was a pretty trashy definition of me, of a dimension, to be honest. I'm trying to think of something better.
Here, let's just do it together. What is a dimension? Well, one way to look at it is it's just a number line, okay? Like, I know not everyone here has had a lot of math experience, but I'm guessing everyone here had to take some wicked basic math class where you learned about a number line. Is that correct? Mariah, Tegan, Mia? Okay. So a one-dimensional construction is a number line. And here, I'm going to mark off tick marks at every 10 centimeters. So I've just created a number line, okay? A number line is a 1D construction. By the way, you might be asking me, why are you talking about dimensions and number lines? The real art of physics is learning how to measure things like position, velocity, acceleration. And to measure those things, you need to have an origin, a place where you start your measurements from. How far away from X am I? Usually you get to choose your own origin. I'm going to choose my origin to be 0. Now, do you guys know the mnemonic device for the metric system? The kids learn it as King Henry's dog drinks chocolate milk. Has anyone ever heard that before? You guys have? I didn't learn that because I'm too old now, but you guys, my students taught that to me. So who can explain what King Henry's dog drinks chocolate milk means?
I remember learning that, but I can't put words to it.
It's the metric
kilo.
Hecta.
Kilo. Oh, hecta, deci.
No, deca.
Oh, deca. Oh, okay. Decameter.
This is deci.
Decimeter, centi, and then milli.
Milli. So Vladimir, if I marked out tick marks in 10 centimeter increments, what is that?
It's a decimeter.
Decimeters. Decimeters. Okay, so 0 DMs, 1 sliding into your DMs on a Tuesday afternoon, okay? So 1 DM,
yes, all right.
2 DM, 3 DM, 4 DM, 5 DM, 6, 7 DMs. I'm working in the strange and unusual unit of decimeters. Now, what I just did there is something kind of important. I created a one-dimensional number line, right? And I chose my own, wait for the loaded term, metric, okay? The metric is a scale that I get to choose because I am the observer. That's the loaded term for the scientist. I am the observer, and I'm going to choose my coordinate system, and I'm going to choose the scale or the increments by which I measure things. We get to decide and impose upon nature what is our idea of a good unit of distance. We might choose meters. We might choose centimeters. We might even choose decimeters, okay? Or light years or parsecs. Hello, Mateus. Okay. In a one-dimensional construction, you can move forward or back. That's about it. How do I go from one-dimensional to two-dimensional? I create a second number line that is, Vladimir likes to say perpendicular. Me, in my fancy vocab terms, I like to say orthogonal. Orthogonal is like perpendicular, but better. That's all I'm going to say about that. And so what I'm going to do is I'm going to create another number line. I'm also going to have a metric in decimeters for that number line. And now, Vladimir and friends, I have gone from a 1D construction to a two-dimensional construction. I added another number line that is orthogonal to the first one. And now I can grid out a set of coordinates, x comma y, that tell me how far I am from the x-axis and how far I am from the y-axis, okay? 2D is a tabletop. How do I get to 3 dimensions? Well, I'll need another number line that is orthogonal to the first 2, that has no components in either direction. Now, I'm working on a 2-dimensional surface. So here I have to use the tricks, the lies of artists to try to imply 3 dimensions. And I'll do that by creating a z-axis. Bear with me, students. And my z-axis will go perpendicular to all 3 of those. And once again, I don't know how the geometry or the perspective works out, but I'll try to mark out decimeters here, okay? So this is my z-axis, which goes into and out of the plane of the board. And now I can mark out points along my z-axis. And now my points are 3-dimensional. They have coordinates x, y, and z. All of this is a way to say, what is the difference? What is the difference between 1-dimensional, 2-dimensional, and 3-dimensional? With each dimension, you get another number line which measures position along that number line. Special relativity, the first thing that we're going to learn today, is a 4-dimensional construction. Students, based on our analogy, how would I go from 2D, from 3D? How could I end up creating a 4-dimensional construction mathematically?
Just add another orthogonal axis.
Add, nice use of mathematical vocabulary, Vladimir. Add another orthogonal axis. But holy shit, Vladimir, I'm in trouble here. See, because I am unfortunately a 3-dimensional human being. So I can make an X, and I can make a Y, and I can make a Z axis, which are all independent from each other. But I can't fathom or figure out, as a puny 3-dimensional human, how can I create a 4th number line that is somehow perpendicular to all 3 of these? Anywhere I put the 4th ruler, it will have components in X, Y, and Z. It seems as if I'm screwed because of my puny 3-dimensional limitations. And yet, just because you can't represent it in 3D space, it doesn't mean you can't think about it. And it certainly does not mean you cannot define it mathematically. 4 dimensions, the construction for it is just as simple as Vladimir said. Imagine another number line perpendicular somehow to all 3 of these. Now, many people have come up with different ways of trying to visualize 4-dimensional space. I have my own, which is peculiar to me. I'm not sure how great it is, but I'd like to share it with you just for fun. And all of this is kind of preamble to our lecture today, but bear with me. Sometimes when I try to imagine the 4th dimension, I try to imagine a 3-dimensional box that contains the entire universe. And then I try to imagine a whole sequence of boxes, right? All which kind of run forward or backwards like loops in a film. So you can imagine that that number line somehow would contain each of these boxes, which somehow contain the entire universe. And if you could watch someone do a pedestrian activity, like if you could watch a stick man throw a ball, then in one frame he'd hold the ball in his hand, in another frame the ball would be moving up into the air, and maybe in the final frame the ball would be resting on the ground. And you could move forward and backwards in time simultaneously. Now, okay, this number axis actually seems to share a component with our x-axis, so it's a little bit of a cheat, but you have to use cheats. There are many other ways to imagine this 4th dimension of time. Many tricks can be done, but that's one of my personal ones. Okay, now it's time for a test to see what you've learned. You know what 1D is, you know what 2D is, you know what 3D is, and you're scratching your brains trying to think about 4D. What's a 0-dimensional construction? What would 0D be?
Point.
Say that, Vladimir?
A point.
He's too good. He's too good for you guys. Look.
You see, I'm kind of cheating because I've been a long time obsessed with 4 dimensions.
Okay. I've got something to tell you, Vladimir. 4D is good for special relativity. Once we get to general relativity, the number of dimensions starts to go up from there, and it ain't pretty, let me tell you. I've got some funny stories to tell you later. Okay, I've got another story to tell you as well. I do have this book on my bookshelf, but I wasn't smart enough to look for it beforehand, and I don't want to go rummaging around because time is precious. I have a slide about it. Before we go forward, I want you to think once more about dimensions in a different, funny, historical way. I want to tell you about this legendary book that always comes up whenever people talk about relativity. And it was
Flatland.
Flatland, right. So the book is called Flatland, and it was written in the late 1800s by, I forget what his name is, Adam Abbott or something. This book is called A Romance in Many Dimensions, and it was sort of an allegory or a thinly veiled critique of Victorian society as told by geometrical shapes that live in different dimensions. So at the beginning of the story, the hero or the protagonist of Flatland is actually a square that lives in a two-dimensional universe. And in this square society, your hierarchy in the society is based on the number of dimensions of your polygon. So if you're a square, you're kind of like an office worker or a civil servant, you know, someone who's working just like a dead-end government job. If you were a triangle, then you would be like a factory worker or a boot black, as they would say, something like that, right? If you were a pentagon, or maybe if you were a, what do you call this, a hexagon, maybe you would be a general in the Navy or in the Army, or an admiral in the Navy. And the more polygons, the more sides to your polygon, the higher and higher you go. Eventually, the highest order of their society was a polygon of infinite dimensions. What would happen to a polygon as you made more and more, not infinite dimensions, infinite sides? A polygon of an infinite number of sides, what would that look like? I guess the more and more sides that you add to your polygon, eventually when you have an infinite number of sides, you would become indistinguishable from a circle. So a circle was actually considered the priest or the shaman of their society. They were the highest ranking you could get. Unfortunately, this was a Victorian society. It wasn't very progressive. So women, unfortunately, they were just lines. Okay, so, all right. I didn't make this up. Don't cancel me, bro. Okay, anyways, so you can see here that now what happens, all of the drama in the story takes place when a three-dimensional sphere, a bona fide three-dimensional sphere, befriends the square and decides to take a visit to Flatland. And the square is saying, man, things are kind of confusing here in Flatland. Because if you think about it, guys, we are three-dimensional creatures, correct? If you live in, say, 3 dimensions, your entire view or perspective of the universe is actually 2-dimensional. For instance, rainbow ball here has many colors, blue on one side, red on the other. But when I hold up rainbow ball to you, you can only see rainbow ball as a 2-dimensional flat projection on your sky or on your camera. It would be impossible as a 3-dimensional creature to simultaneously see all sides of the rainbow ball at once. If I was a 4-dimensional creature, however, I might be able to do that. A 4th-dimensional being, if such a thing could exist or does exist, would see all sides of this at once. If you're a 2-dimensional creature, everything you see in your field of view is fundamentally 1-dimensional. And the square complains about this because he says, you know what's scary? It's really hard to tell the difference between a circle, a priest, and a woman in my society, because seen from my perspective, they actually kind of look the same. From my perspective, a woman looks like this, and from my perspective, a priest looks the same with maybe only a little bit of shading differences. Maybe the line that makes up the priest is a little brighter in the center. You know what I mean? Like if you're an artist, when you draw a sphere, it's a little brighter in the front. So he's saying you got to kind of use shading differences to tell the difference between people, because everyone kind of looks like a line and it's confusing. All right. To make a long story short, the three-dimensional sphere decides to visit Flatland. What do you think the sphere looked like to the two-dimensional construction of a square? Well, let's try to vision it, right? So at first, this is Flatland to the sphere, and the sphere, as it reaches through and does a cross-section of Flatland, it touches the point of its sphere to Flatland, and at first, it looks like a dot. And then, as subsequent slices go through, the sphere became a line that grew in shape and size until it reached some maximum diameter, and then, as it passed through, disappeared. That's sort of what a sphere, I should round that a little better. That's what a sphere would look like to two-dimensional creatures in Flatland. Okay, now you try it.
But it's not like all of them at once. It's one cross section at a time.
Right. So it starts as a dot, it grows, and then it shrinks. So it would probably look like this in time. It would look pretty weird. Hey, what if there was a four-dimensional sphere, a so-called hypersphere, and a hypersphere were to pass through our three-dimensional universe? Can any of you conceptualize what that would look like? What would it look like if I watched a hypersphere pass through my three-dimensional world? By analogy.
Should I ruin it for everybody?
Go ahead, Vladimir.
I'm not going to answer.
Well, you're going to have to talk over the din of other students trying to compete to answer the question, but I think you've got it in you. Okay, so go ahead. Tell us what you think.
It's going to be a point, then a small sphere appearing out of nowhere. Then when the hypersphere reaches its maximum diameter, it will be a big sphere. Then it's going to get smaller, then to a point again.
Right. It would be like a three-dimensional version of that. That makes good sense to me, Vladimir. That would probably look pretty crazy. It would look like a dot that grew into a sphere in front of your eyes and then shrunk back down. I have 2 points to this whole preamble. It's hard to think about 4D, but that doesn't mean it's not fun, okay? No bitching about 4 dimensions, because it's fun. It's fun to visualize these things. And there are people out there on the internet, you can look up tesseracts and other things like that who've tried to imagine this. Okay, so how did we get ourselves into this mess?
Wait, but isn't it true that a person, like people's minds, people's brains, just are not hardwired to see the 4D as it is? We can only imagine cross sections.
You can imagine anything with sufficient training and imagination. Well, I guess, no, you're not hardwired to think 4D.
No, I mean, you can imagine Tesseract as being embedded in 3D, but you can never see Tesseract as it is.
Yeah, I don't know. It's like, that's like saying, Vladimir, have I ever truly seen a sphere before? As a two-dimensional creature, I'm sorry, as a three-dimensional creature, I've only seen spheres ultimately as two-dimensional projections.
Yeah, but like you are,
I can't imagine it.
Yeah,
right?
but so you can spin it in your head to create, to like understand that it spins as 3D, but you cannot do the same in 4D.
Well, let's agree on this. It's difficult. It's complicated. Okay. I don't want to say what can be or can't be done by anyone, because people tend to surprise you, you know? But I agree, it's difficult.
Fair enough. Fair enough.
Okay, so in order for me to explain the fourth dimension of time to you, we're going to have to start with some kind of boring quotidian concepts. Believe it or not, I need some vocabulary words so that I can properly help you understand this. And we're going to have to talk about a basic problem in physics, which is measuring the motion of an object. It could be a star or a planet or a galaxy relative to some coordinate system. Usually in astronomy, we're concerned with Earth as the origin of the coordinate system, and we're measuring the motions of stars and galaxies rather relative to Earth or the sun. So I want to talk to you guys about inertial reference frames and velocities for a second. And you're going to have to bear with me on this. So let's imagine we were going to do something boring, like watch a skate punk take a little skateboard ride across our classroom. Okay, so I know you kids are into skateboarding because I see you out in the streets all day. And let's go ahead and let's construct ourselves a coordinate system. If we were still in classrooms, this could be a classroom coordinate system. And we'll take one corner of the room and we'll make it the origin. And I'm going to put an observer at the origin. And because this is going to get tricky as we go forward, my observer is going to be called A. That's the student who stands in the corner of the classroom and watches his buddy take a little skateboard ride across the room. This is a common problem in physics and astronomy because we have to measure the speeds and velocities of moving objects like stars to comprehend them and to learn about them. Let's call the moving skateboard observer observer B. And I'm going to give him a typical skateboard speed. I think in the metric system, maybe 5 meters per second would be a reasonable skateboard speed. A human being walks, Vladimir, having been born in Russia, you might be able to correct us here. I think a human walking speed is about 1 meter per second. Does that sound right, Vladimir?
Maybe a tad faster, but that's pretty good.
So you would say this is a reasonable skateboard speed?
Yeah.
4 or 5 times what a walking speed is. Okay. We have a coordinate system constructed by A, the classroom system. And if you think about it, B is on his own little cosmic journey through space, and B constitutes a different coordinate system, a moving coordinate system. If I wanted to, if I was weird enough, if I was weenie enough, I could attach a little flagpole to his skateboard, and that flagpole could be a kind of origin or an axis point. And observer B could say that his moving skateboard constitutes a second moving coordinate system relative to the first. And this is the problem that humans and aliens on some other planet might have moving with respect to one another. I need to define a concept. So the A coordinate system is a reference frame. So a coordinate system is basically another way of saying a reference frame. It's basically a set of axes, X and Y, that allow you to plot motion. I now want to define an important term in relativity, one that I need to refer to all the time. It's called an inertial reference frame. An inertial reference frame is defined as basically a coordinate system or a reference frame. Let me use abbreviations here so I can get through this quickly. A coordinate system with a, here's the tricky part, a constant velocity, Gesundheit. An inertial reference frame, which I'll sometimes refer to as an IRF going forward, is a coordinate system with a constant velocity. Class, does observer B constitute an inertial reference frame? Yes or no? I'm pitching you a softball here, class.
Yes.
Yes, Mariah, because it's traveling at a constant velocity. Hey, Mariah, does observer A constitute an inertial reference frame?
I mean, isn't he just standing there?
Yes.
So I would say no,
Why not?
because he's just standing.
What's his velocity?
0.
Is 0 a constant?
I mean, okay, yeah.
So do you want to revise your answer?
I would say yes.
Exactly. You have to think about that for a moment. Never forget, students, that even if your velocity is 0 meters per second, that is also constitutes an inertial reference frame. So then we both agree that observer A and observer B constitute inertial reference frames, correct? That's an important first concept. Can you guys give me an example of a non-inertial reference frame?
An accelerating racing car.
Yeah, an accelerating racing car. Or if you ever been to the amusement park where you go on the teacups or you go on that little rotating gyrotron.
Yeah, so everything that travels in like circles, it's not an inertial reference frame, right?
Correct.
Because
We're gonna
even
have
if their speed is constant, there's an angular acceleration.
Exactly, or a centrifugal acceleration. We're going to have to deal with that later, Vladimir. So for now, for now, don't think about that too hard, or you're going to start to get the willies. Okay. Okay. Now you guys know what an inertial reference frame is. I now need to talk to you about how we add and subtract motions. The issues of relativity come about because there are two observers, both in inertial reference frames, but different inertial reference frames, and they have to describe the same sequence of events, and that's when shit starts to get confusing. For instance, let me start real simple and dumb with you guys, and let's imagine a scenario where observer B takes a sort of a little blue tennis ball, okay? And observer B takes a blue tennis ball and is going to throw it forward relative to observer A. And from B's reference frame, he's going to throw this ball forward at 2 meters per second. Can you guys tell me the speed of the ball according to observer A? This shouldn't be hard.
7 meters per second?
Yeah. And let's think about what Mateus did there. Mateus said the skateboard's traveling at 5 meters per second, right? And relative to B, the ball travels at 2 meters per second. Oops. I'm going to eat that for lunch later, so hold on. Plus 2 meters per second. And then Mateus adds 5 meters and 2 meters per second. He gets 7 meters per second. Now, let's say I don't want this to just be considered in speed terms. What if I want to consider it as a velocity? Do you guys remember the difference between a speed and a velocity?
Speed is a scalar quantity, and velocity is a
Vladimir,
vector.
let's use simple words here. We don't want to get the kids confused.
So speed doesn't have a direction.
But velocities do. Can I make a one-dimensional construction of velocity, Vladimir?
Sure, you can, I believe.
Because I could have
No?
direction to the right or direction to the left, right?
Yeah.
Positive or negative. Let's use directional vectors to make this a little more sophisticated. In my problem, the skateboard travels 5 meters per second to the right. Now, I want to talk to you guys about what I'm doing here because it's a little advanced. Do you guys see how I put a little hat over the R? In mathematics, they use that hat to say, R isn't really a variable. It specifies direction, okay? The skateboard travels 5 meters per second to the right. The ball was thrown 2 meters per second to the right. And therefore, according to observer A, the ball travels 7 meters per second to the right. All of this should be common sense. But in this case, there's a name for common sense. This thing, which Mateus did quite naturally, is known in physics as the Galilean transformation of velocities. The Galilean transformation of velocities, because Galileo first described this issue in physics. In some ways, the Galilean transformation of velocities is just common sense. In other ways, common sense is not always so easy to follow. For instance, suppose I mix the problem up for you. Suppose observer B were to take a red ball and throw it 2 meters per second to the left. 2 meters per second to the left. Can you guys tell me the speed and direction of the ball relative to observer A? I need a better red. Hey, Mateus, you were so good at this before.
Sorry, can you repeat the question? I was writing down.
Sure, Mateus. Observer B throws a ball 2 meters per second to the left. What is the velocity, speed, and direction of the ball relative to observer A?
3 meters per second?
Which direction?
To the left? Oh, that's good.
Got you. What's the correct answer? No?
I
I thought
don't
this
even
was
know if
common
it's to the left.
sense. Common sense is common. It's easy, right?
Wouldn't it seem like it's kind of like almost, it's not stopping, but it's not really going like, I don't know. Because there's like a conflicting forces. Because he's going that
Well,
way
there's
and he's starting.
conflicting directions, not forces yet.
Right.
We'll get to forces. Let's write it out in mathematical terms. Let me explain how the Galilean transformation of velocities is supposed to work. The velocity of the skateboard, and I'm talking velocity, mofos, not speed. The velocity of the object relative to observer A is the velocity of observer B's inertial reference frame plus the velocity of the ball, which I'll just leave as V so I don't get confused here. So let's consider the velocity of the skateboard. The velocity of skateboard is 5 meters per second to the right, plus the velocity of the ball, which is 2 meters per second to the left. And yet, in order to add these two, we should probably have the same direction. Luckily, I know something that's also common sense. Right is the negative of left. So what this really is 5 meters per second to the right minus 2 meters per second to the right. That was fair, right? What I did there was fair. In other words, yes, Mateus, the ball is going to travel at 3 meters per second, but not to the left, to the right relative to observer A. Did that make sense?
Yes.
You had to think about it slowly and carefully, though, didn't you, Mateus? Sometimes common sense isn't so common. That's why we had to give this a special fancy vocab term like the Galilean transformation of velocities. I would like to point something else out before we move forward. Do you guys agree that this is true? Observer B claims the ball is moving at 2 meters per second to the left. Observer A claims the ball is moving at 3 meters per second to the right. Do you see that? Two observers in different inertial reference frames are not always going to agree on the description of events. The same thing is happening, whichever reference frame you're in. The ball is going that, well, all right, it depends on who you're talking to, right? Relative to observer B, the ball is moving that way. Relative to observer A, the ball is moving away from the origin because it's being carried faster by the skateboard. What I'm trying to do is condition you guys to be comfortable with the fact that two different observers in two different inertial reference frames are not always going to agree on the same description of events. And things are going to get weirder from here, okay? All right, you've just digested some important preliminary concepts. I need to erase. Let me know when I can do that. Y'all good? All right. Now, let's talk a little bit about the speed of light. Here's what I'm going to tell you today. You know that Galilean transformation of velocities that you just learned about? That's been the bedrock of how physics works for hundreds of years. It's been successful at describing a variety of physical situations. But actually, the Galilean transformation of velocities is false. It doesn't actually work. Okay, right. All right. Let's take a learn about how. I want to talk to you guys about a number that you've seen many times in this class. It's called the speed of light. And it's so important to physics that it gets its own variable, c. Do you guys remember what it is?
3 times 10 to the 8 meters per second.
Up to now, that's been a pretty useful version of the constant to have. Today, we're going to see that there is a better version, more helpful sometimes, I like to see it in kilometers per second. In kilometers per second, the speed of light is 300,000 kilometers per second. That's a pretty good version that we're going to be using today. There are other ones that I'll introduce later on in the class. This is considered the fastest speed that's allowable in nature. And the reason why has to do with relativity, which you're learning about today. This is so fast that if you ever tried to observe it on your own, it appears to be instantaneous, right? I can click the button on this laser pointer, and the dot appears pretty much instantaneously. People had speculated that perhaps it takes time from light to go from one place to another. And do you want to know who the first person who attempted to measure the speed of light was? That totally greatest of all experimental physicists, Galileo Galilei. And here's what he did. He said, you know, all we need, guys, is a really long baseline. So he got a friend of his and he said, let's go to two different mountaintops that are separated by a whole bunch of kilometers. And what I'm going to do is I'm going to go to the top of the mountain at midnight, and I'm going to hold a lantern up. And at exactly midnight, I'm going to open the shutter doors, and I'm going to shine the beacon towards you. And what you're going to do is you're going to climb the other mountain, and you're going to observe, and you're going to record the exact time that you see the flash. And we'll use the difference in time to calculate whether light has a velocity. So he goes up, he opens a lantern, and then he comes back down from the mountain, and he says to his buddy, what time did you see the flash? And he said, exactly midnight. So Galileo had a right to conclude observationally that the speed of light was infinite. But Galileo was smart and he had good intuition. So even though he had the right to claim that, he said, it could be, he wrote in his journal, that the speed of light is so exceedingly fast that this is still not a sufficient baseline to measure it. And he was right. Later on, a famous, I believe he was a Dutch astronomer, came up with a much more clever way to measure the speed of, yeah, what a champ, I agree. Hans Olmert, I believe it was, came up with a way cooler way to calculate the speed of light. And just try to think about how neat and clever this experiment is. He observed the moons of Jupiter at two different times in Earth's orbit. Now try to contemplate this. Here's Jupiter, and Jupiter has a moon, Io, which has a period of about 42 hours. You've probably heard me talk about it, right? So what happens is if you watch Io with the telescope, and I've done this many times, you kind of see Io getting closer and closer to Jupiter. And then if it's, say, at the part of its orbit where it's going to go behind Jupiter, you see it disappear. And then several hours later, you see Io appear out the other side. And you know from observation the exact number of time, just the length of time that it takes for Io to travel behind Jupiter. Let's say it's like, I'm just going to make something up right now. Let's say it's 10 hours, or it's probably 8 hours or something smaller like that, okay? The idea that he had, and when I learned about this, I thought it was so clever, is if this is the sun and this is the orbit of Earth, and remember that Jupiter is about 5 AU from the sun, what he did is he measured the time that it took Io to go behind Jupiter when Earth and Jupiter were in opposition. So Earth was really, really close to Jupiter, right? And then what he did is he waited until Jupiter had moved over here and Earth had basically moved 2 astronomical units away. And he observed the period of time that it took for Io to go behind Jupiter. And sure enough, he found that instead of 10 hours, it was like 10.02 hours. And he ascribed the difference in the time lag to the difference it would take light to travel the 2 + 4 more AU, which is a much more significant baseline. And he actually got a value that was basically super close to 300 kilometers per second. So he was one of the first people who, what a genius observation. You know, that really inspires me. Anyone with Galileo could have done that if he had been clever enough to think of it. That's what I love about that. It was sitting right there, waiting to be discovered. There are so many things like this in science. Today, we have way crazier ways of measuring the speed of light. In fact, the way it, believe it or not, the speed of light is one of the highest precision measured constants in all of physics. We know so many significant figures of the speed of light that we eventually gave up on measuring them, and we just flat out defined all of the other measurements in physics based on the speed of light. So just wait till you see how crazy this is. You can't make it up. Today, if you look up the speed of light, the International Physics Union, the union, or the International, the American Physical Society, whichever body of physicists, I know about the IAU more than I know about the physics societies, but we have today defined the speed of light to be exactly 299,792,458 meters per second, and then wait for it, we have redefined the meter, and we even redefined the second in terms of the speed of light. That's how high precision we've measured the speed of light. If you look up the definition of a second, look at this. We have today defined the second is defined as being equal to the time duration of 9,192,000,000 periods of the radiation corresponding to the transition of the two hyperfine levels of a fundamental unperturbed ground state cesium-133 atom. In other words, they're basically defining the second itself off an emission line coming from a cesium atom. Okay, so this is nuts. How do we know the speed of light to such a grand degree of precision? Because of another ingenious device, a physics experiment that I need to tell you about, okay? So bear with me here. I want to introduce you to this thing known as the Michelson-Morley interferometer. Gesundheit. I need to do this for reasons which are hard to explain right now. Okay, just take a look at how nutty physics can get. I designed myself a measurement device with a laser, and the laser fires forward through something called a half-silvered mirror. And half-silvered mirror will transmit 50% of the laser beam through the mirror, and it will reflect 50% of the laser beam perpendicular to it. Now what I do is I put two mirrors at some distance from the half-silvered mirror. Mirror A is fixed in position, but mirror B can have a fine degree of precision movement with a really, really hypersensitive threaded screw. And if you have enough threads in the screw, you can move the mirror by microscopic amounts, like micron amounts with each twist of the screw. What I do is I fire the laser through the half-silvered mirror. One half of the beam hits the fixed mirror, bounces off, hits the half-silvered mirror, and 50% of that beam travels to this screen. Meanwhile, the other path of the beam hits the movable mirror, bounces off, and 50% travels through. So the two laser beams line up again. If I move the mirror by a microscopic quantity in distance, the two waves of light will become slightly out of phase. So instead of traveling the exact same distance, one wave travels a little bit longer than the other, and the two waves, I'm not drawing this very well, they're out of phase with each other. And what they do is they create a diffraction pattern. I don't know if I put it inside the slideshow, so allow me to look up for you just so you can get a sense of what it is. I want to type circular diffraction pattern with a laser. When the two lasers strike the screen, sneezes are going around here in this house. This is what it looks like. And believe it or not, oh shoot, this is what the diffraction pattern looks like when it hits the screen. What's so clever about this experiment is you can measure the distance between the bright fringes, and that will tell you the difference in distance the two lasers traveled, and that lets you calculate the speed of light to a wicked, wicked high degree precision. Because what you do is you get some machinist to drill you out a really, really sensitive screw so that microscopic turns of the screw, you're basically translating the fact that you can make really, really precise measurements in distance and converting that back into a speed by measuring the difference in path. Totally ingenious device, wicked awesome.
But the speed of, we technically know only the average speed of light, right? The two-way.
I'm not sure what you mean by the average speed of light. You're gonna have to help me understand your question.
So the speed of light was never measured one way,
Well,
right? It was only measured two-way.
I gave you three different methods: the mountain method, the Jupiter method, and now the Michelson-Morley interferometer. But you are measuring the speed of light, Vladimir. I don't think it's more complicated than that. Don't let it be complicated. It's going to get complicated enough as we go forward, okay? All right, just trust me. Take a leap of faith for now. Now it's time to talk about Albert Einstein. So the first topic that we're going to cover today is special relativity. Special relativity was proposed by Albert Einstein in the year 1905, before he was a famous physicist. And the problems that led Einstein to propose this special relativity were because of problems associated with measuring velocities at the speed of light. As people began to measure the speed of light to a high degree of precision, they began to notice that there were some funny things going on when you measured the speed of light relative to a moving object. One of the funny ideas that Albert Einstein had when he made up his thought experiments is he realized that if things could travel at the speed of light, observations would start to look pretty weird. For instance, imagine you could observe a game of catch, you know, where you like throw a ball back and forth between two observers, A and B, and you are going to be observer C, kind of watching A throw a ball to B. Normally what happens is A throws the ball, it travels through the air, and then at some time later, B catches it. What if A could throw the ball faster than the speed of light? What would that look like to observer C? Well, A would throw the ball, but the light from it would actually move slower than the ball did. Since observer B is closer to C, first, the ball would seem to be caught by observer B, and the light from the catch would reach C. Then the light from it traveling through the air would reach C. And at last, the light of it being thrown would reach C. So if you could throw a ball faster than the speed of light, the whole thing would appear to run in reverse according to observer C. Time would appear to run backwards because you'd see the ball being caught before you saw the ball being thrown. And Einstein felt that that was deeply observing, that cause and effect would appear to be reversed if objects could travel faster than the speed of light. That does not prove that it cannot be done, however. It just means it's weird, right? Here's what does prove it cannot be done. We have a definition of light from our earlier chapters in this class. I don't suppose any of you remember what the fundamental definition of light is, do you? What are photons made of? What is light?
You said photons are ripples in the EM spectrum.
They're, yes, ripples in the electromagnetic field. Electromagnetic field. And the technical definition of light, according to our class, according to any physics class, is a time-varying electromagnetic wave. In other words, there's a magnetic field component, there's an electric field component, and they wiggle through space, like you see here in the bottom animated GIF. It's time-varying because it moves through space, and it's a wave because it has wave-like properties, wavelength and frequency and so forth. Here's a mechanical wave. Einstein then imagined the following scenario. What if you could ride on a skateboard at the speed of light? and you could travel alongside a photon, you would quickly find yourself in a whole bunch of trouble, and here's why. As you traveled along your time-varying electromagnetic wave, the wave would actually appear like this. It would appear frozen in time because you and the electromagnetic wave would have the same velocity, c, and therefore it would become a static electric and magnetic field. Here's the problem with a static electric and magnetic field.
You'll be blind.
Huh?
You'll be blind.
No, it's not that you'll be blind. It's that the photons, the energy of the photon will disappear.
Oh,
Remember, students, that we defined the energy of a photon as Planck's constant times the frequency, where the frequency is measured in some number of cycles per second. If you could travel alongside a photon, the cycles per second would go to 0, and as the frequency of light went to 0, the energy of light would go to 0. If you traveled at the speed of light, the energy of photons would disappear. And that deeply bothered Einstein because he did not want to believe that if you traveled at a certain velocity, the energy of light would disappear from the universe. That would violate one of the bedrock principles of relativity, principles of physics, the conservation of energy. Do you guys sort of follow what I mean there?
wait, the world would literally what, fall apart?
Well, it's not that the world would fall apart. It's just that things wouldn't work.
Yeah,
Things-
because
think
if light
trying to
disappears for you,
taking too
does
long
it disappear for everybody else, right?
Boy, I'm running out of time here.
Uh,
There's one third issue. Yeah, it wouldn't disappear for everyone else, but it shouldn't disappear for anyone, Vladimir. There's one last issue, and Einstein claims to have not known about this. There was a legendary experiment known as the Michelson-Morley Experiment, conducted by the same people that designed that cool interferometer that I told you about a few slides back. One of the confusing things about light is that light is a wave, and most waves have a medium. For instance, if you make waves on a rope or a string, the medium of the wave is the string. In an ocean wave, the medium is the water. Sound is a wave. What's the medium of sound?
air.
Air. They're vibrations in air. Scientists were really concerned that they knew light was a wave because it had wavelength and frequency and it exhibited interference and diffraction. But if all waves up to now have media, how do waves of light travel every day from the sun to the earth through the vacuum of space, which is supposed to be the nothing, right?
So the media is the space-time itself.
Well,
No?
that's what they started to think at first, Vladimir. They got so paranoid that light was a wave traveling without a medium that they imagined space itself somehow constituted a magical medium that could not be seen, smelled, observed, or tasted. In other words, space wasn't the nothing. It was the nothing that was somehow a something that they couldn't quite touch or grasp. They even invented a name for this medium of space. Do you want what they called it? They called it the superluminiferous ether.
Okay.
And I want to explain what's really going on here, because in Aristotle's physics, the primeval elements of Earth were earth, wind, water, and fire. But because the Greeks believed the heavens were different than the earth and were more magical, they believed there was a fifth element that all the heavens and planets were made out of, called ether. Now, in the olden days, when you were a philosopher, instead of actually doing science and making observations and measurements, it was considered classy to quote the old philosophers as a way of justifying your bullshit. So what these guys were essentially doing is reverting to like 0 AD science, where they were basically
source.
Aristotle because they couldn't understand how light was traveling from the sun to earth. In other words, ether was a way of saying, there's some bullshit out there and I don't know what it is. It was a very elegant and classical way of saying, I don't know what I'm talking about, all right? They also put the word superluminiferous in front of it, which confuses people even more. Very helpful, okay? If you can't, so trust me, bro, pretty much, okay? They attempted to do one experiment which they believed would conclusively prove that the ether existed. And I want you to think about how clever this is. What they did is they first got a pretty good idea of Earth's velocity. Earth travels on almost a perfect circle around the sun. So let's say that Earth has a pretty constant velocity around the sun. And weirdly, the velocity of Earth around the sun, if you put it in kilometers per second, it turns out to be 30 kilometers per second. So wait for this one. They decided to fire 2 laser beams. Let's let one laser beam, the blue one, travel towards the sun. This laser beam does not have any additional motion due to Earth because it travels perpendicular to the direction of Earth, right? Okay. So they believe that if they fire this laser beam, the speed of the laser beam should measure out at 300 kilometers per second. Then they fired a second laser beam in the direction of Earth, tangent to its motion. So in other words, they fired a green laser beam in this direction. According to the Galilean transformation of velocities, what speed should they have expected to measure for the laser beam that is green?
300,030 kilometers per second.
Right, because you have the speed of light plus the speed of Earth. That makes sense, right? You're going to add the velocity of Earth to your laser beam. And by the way, that measurement, if you think about it, this is 1, 2, 3, 4. So this is 1 part in. So that's 1. Yeah, that's a measurement of 1 part in 10 to the 5, I believe, right? A 1 in 100,000 precision. And although that's a sensitive measurement, that's doable in a modern physics lab. And by the way, this famous experiment is known as the Michelson-Morley Experiment. And it was conducted shortly before Einstein's theory of relativity. It was like maybe 5 or 10 years before, 1887. I really should know the date of the Michelson-Morley experiment, and I'm forgetting it. I want you to forgive me. Luckily, we have the world's repository of knowledge at our fingertips. Michelson-Morley experiment. You can read a little bit more about it if you're ever in the mood for it. 1880. Oh, did I say 1887? I guess I know more than I thought. Okay, so it's about 1887 when they did this, a few years before Einstein. Now, here's what's crazy about this. I want to show you what happens to you when you start going down the rabbit hole of physics. This ends up being your job, and I want to show you a picture of it. I think they performed the experiments like at the University of Colorado. Here you can see the Michelson-Morley interferometer, where they have the half-silvered mirrors and they have the 2 movable mirrors in the screen. But this measurement was so sensitive and so precise that in order to damp out vibrations from trucks nearby, they put the thing on a gigantic block of granite so that the mass would damp the vibrations. And here's another problem that you might not have thought about. How do you figure out which direction is towards the sun and which direction is perpendicular when you are sitting on an Earth which is doing this every 24 hours as you move around? So how did they get around this? Wait for it. They suspended the block of granite on a pool of liquid mercury. And then as they ran the experiment, they spun the granite block, arguing that 50% of the time it'll point towards the sun and 50% of the time it'll point away. And they won't know exactly which one, but it'll make an oscillation and they will plot it. And that's how you measure the speed of light. Damn, it's cool to be a nutty physicist, okay? It's that or it's punching into your office cube. I don't know what you guys think is better. I know which one I prefer. Anyways, do you want to know what they found when they performed the experiment?
I bet it didn't work. It was still 300,000. No?
Exactly. No matter which direction the laser was being fired, it always turned out that the velocity of the laser was c, 300,000 kilometers per second.
Just light here defying everything.
It's basically what happened is they broke the Galilean transformation of velocities, which was supposed to be common sense. It was supposed to be Ladoy, as Wayne's World guys say, like it was, or no, Bill and Ted. I can't remember who did it. Doesn't matter. It was the velocity of light was supposed to be the velocity of the laser plus the velocity of Earth. But it's as if the velocity of Earth did not affect the speed of laser. And what they actually published, normally when your experiment fails, you're not allowed to publish those results because you failed, okay? But this failure was so profound in its implications that they published the results, and no physicists at the time had any idea what to make of it. A few years go by, and along comes Albert Einstein. Albert Einstein is sitting around thinking these deep thoughts about how it would be awful if you could travel at the speed of light. And he decided to write a little monograph to his local newspaper. And you got to think about how different newspapers were. Today, we have astrology columns in our newspaper. And then random people could send letters to the editor about their theories of the speed of light. And that was cool to publish, right? So I don't know if we're going towards idiocracy or what it is, but I certainly would like to live in a world where kooks could publish their crazy theories of physics to the local newspaper. In 1905, Albert Einstein proposed that the whole issue of the speed of light could be resolved if we radically reversed our thinking and just assumed that these two postulates were true and explored their consequences. And these are things that I want you to know about. They're known as the two postulates of special relativity. I'm kind of running out of time, but we're going to take them as notes. Then I'll explain their consequences, okay? Okay. So introducing the postulates, the two postulates of special relativity. Einstein published them in a newspaper in 1905. The first rule goes like this. The laws of physics are the same in all inertial reference frames. This was not a controversial statement. The idea behind this postulate, and the reason why he felt it necessary to state it out loud, was to let people know that the laws of physics, like conservation of energy, or the nature of photons, or the force of gravity, they should not shift or change depending on the motion of the observer. If I travel on a magic sleigh ride through the cosmos, gravity shouldn't function differently. Light shouldn't disappear. Everyone was cool with this postulate. It seemed like that wasn't even worth stating. It was the second postulate that caused some troubles. He claimed the speed of light, c, is the same for all observers. And I don't need to really say this, but regardless of velocity. That's observers, if you can't read my handwriting.
What a brilliant assertion.
Yes. Now, In mathematics, we have to explain this term postulate to you guys. Sometimes it's difficult to prove a thing that you intuitively know is right. So you instead phrase it in the term of a postulate. You say, let's suspend disbelief for a moment, and let's propose this is true, and let's explore its consequences. If we find the consequences agree with observation, then you will start to believe me more. In other words, if you think about Euclid's The Elements, which is the basic foundation for basic geometry, I think a postulate could be between any 2 points, you can connect a straight line. That seems to be like a reasonable assumption. It's sort of difficult to prove it in the first place, but you say it's true, and then you kind of let it sit with you over time, something like that, you know? Once Albert Einstein proposed this, people got a sort of titillation from it, but they, of course, people being skeptical, did not believe him. And they slowly began exploring what the consequences were, and frighteningly enough, they started to discover that they were agreeing with observation. In fact, he also said in his monograph, the whole idea of a superluminiferous ether is totally unnecessary. The vacuum of space can still be a vacuum of nothingness. Light propagates through it if you can agree that the speed of light will always be the same. And let's think about why this is so darned bizarre. If you agree that these two things are true, imagine we performed that same experiment from earlier in our class on the skateboard. Observer A stands at the origin of the classroom. Observer B travels on a skateboard. And now I'm going to let the velocity of the skateboard ramp up to the speed of light, 300,000 meters per second. And now I'm going to put a flashlight or a laser beam into B's hand, and I'm going to let B flip the switch and fire a blue laser pulse right out of the skateboard. B will measure the speed of light to simply be c, because according to B, he can kind of consider himself be at rest with respect to the skateboard, and he can watch the laser beam kind of fire forward. All right. If the Galilean transformation of velocities were true, the speed of the laser relative to A would be the speed of the skateboard plus the speed of the laser. It would end up being twice c. But Einstein says, nope, it's still got to be c. What does AC happen when B flips the switch? In a way, nothing. B and the laser beam stick together, and the laser beam never actually leaves the flashlight because B and the flashlight laser beam have the same speed of c. In other words, the velocity according to A has to be c. The velocity for B has to be c. That means things are buggy when you can travel at the speed of light. One of the things that this seems to suggest is that the velocity of c is basically an extreme limit in physics. It's the fastest speed that is allowable in physics, and nothing, not even light, can travel faster. Okay, let's see how my time is. Oh my gosh, I'm 1:35. Class, we're going to do something a little bit different for today's lab. Today's lab was supposed to be a kind of classic problem in relativity called the twin paradox, okay? Now, all you need for today's lab, we're not going to use any special equipment. We're just going to use pencils and paper and calculator, and we're going to do a classic problem in physics. But I've got some funky ideas about how I want to do today's lab, and hear me out. The math problem that we were supposed to do, all of the stuff that you learned so far is kind of foreground to relativity, and then we start getting into the equations and doing some practice problems and things start to get weird. The next step that I was supposed to do, the logical sequence, was to derive a famous formula called time dilation and show you some of its consequences. And then during our lab, what we were going to do is we were going to do an example in this called the twin paradox. Now, I could jump over that next logical step and I could do the twin paradox as anticipated. But what I think we might want to do today, if we want to stay contiguous, is we'll take a little break. And instead of me deriving, or instead of me showing you an example problem using the twin paradox, we will instead derive the formula for time dilation. Basically, it'll be something like a combo between a lecture and a solving a problem. And what that will do is buy us enough time so that on Thursday's lecture, we can learn the weirder and weirder, cooler stuff that builds up towards black holes. We have to do this because we're running out of time in our class and we want to learn about all this awesome shit. You see what I'm saying? So whether we do twin paradox or the derivation of time dilation, it'll kind of amount to the same for you guys. We'll do a little math problem on the board together. We'll think through it. We'll talk about it, and then we'll stop. The whole thing will clock in under an hour, maybe even 45 minutes or so. Sound like a plan? I'm leaning towards the time dilation derivation so that you're not just getting this big gap in your knowledge, if that's okay with you guys. All right. All right, so let's do that then. The current time is 1:40 iPhone time. At 1:55, we'll kick back in and we'll try to wrap up before 3 as usual, okay? All right, that's our plan. We're sticking to it. I'll see you guys in a little bit. Okay, friends, welcome to lab number 10, where we're going to be doing something a little bit different today. We were already going to do something different, but now we're going to be doing something different than something different that I had originally imagined. So hear me out on this, okay? What you're going to turn into me today is just a sheet with whatever I do on the board, okay? And the purpose is that it's somewhat difficult to do experiments in relativity, and we still have a lot to learn and not a lot of time left to do it. So this makes sense from my point of view. So your name, AS1020 would be helpful. And today, what we're going to be doing is lab number 10. I need you guys to put this because people keep turning in the wrong labs and homeworks in the wrong slots. Originally, our lab was going to be on the twin paradox. And I might still include some of that. But what we're instead going to do is we're going to prioritize deriving a legendary formula, and legendary for being weird and cool and confusing all at the same time, deriving a formula known as time dilation. Here's my argument. We need the formula for time dilation to teach you the twin paradox. So rather than jump over this, because we didn't quite get to it in the class, I had a little too much fun with you guys today. Rather than leapfrog over this to get to the twin paradox, which is going to leave you confused, we're going to spend some time carefully deriving time dilation because it's such a preposterously weird result. And then at some later point, maybe at the end of lab quickly, or maybe next time, we'll cover the twin paradox in its own way, all right? This makes sense, and I think it'll be the most pleasurable for you guys as well. Okay, so one of the things that we're about to learn is that once you've learned the two postulates of special relativity, there are something called consequences of the postulates of special relativity. In other words, if we assume that Einstein's two statements are true, and we explore those ideas, we come to some sort of nutty conclusions, things that don't seem to make sense, but actually bear out during an experiment. And the number one consequence of special relativity that's just totally mind-bendy and messed up to students your first time around, the number one consequence, and I'll teach you more of them on Thursday, but the number one consequence is called time dilation. And what time dilation essentially means is the following statement. It means moving clocks run slow compared to an outside observer. Or the short version, the mantra that I'd like you to keep in your head is time dilation means moving clocks run slow. And there's actually a formula that lets you calculate the different rates of time for the two observers. When I was first presented this as a young physics student, I remember thinking, WTF, how the hell did Einstein just pop this out of his head, go from zero to crazy? I couldn't fathom or understand it, but honestly, they probably had a derivation in the book that I didn't read because I was too busy doing something dumb that an 18-year-old would do, right? Not that I do anything like that today. I'm much more sophisticated. Okay. Anyways, okay, so I want to show you a derivation, and hear me out on this, guys. Up to now, I've tried to not bore you with math details. When a classic formula that you kind of need to know comes up, I just give it to you and I say, it's the truth, and we accept it and we move on so we can talk about cool stuff. But just this one time, I want to show you a mathematical proof, okay? I want to derive this with you because when you see the formula and you calculate the results, you're going to be astounded and you're not going to believe me. And I feel like if we derive it together, you'll be trapped and you'll have no choice but to believe me. That's my trick, okay? Now, in order to do this derivation, this proof, I'm going to require you guys to know two basic formulas from like basic high school math that I'm hoping y'all know about, okay? One is the elementary and very simple distance equals rate times time. Have you all seen that before? Like, I don't even know how you could get through high school without learning distance equals rate times time. Even if you didn't take a math class somehow, you'd still have heard of that because it's like life, right? So that's the first formula you're going to need. The second formula I'm going to require you to know about is the Pythagorean Theorem. And I'd like to imagine that anyone who made it through high school would know the Pythagorean Theorem. Do you guys know that? What is it, Tegan? Tell us. Can you remember it?
It's a squared plus b squared equals c squared.
That's correct. And what do a squared and b squared and c refer to?
The sides of a triangle, a right triangle.
A right triangle. Look at you guys. Y'all pretend like you don't know math, and then you have stuff like that tucked away up in your head. Okay, so it's the sides of a 90-degree triangle where A and B represent the legs and C represents the so-called hypotenuse. Today, kids, we're going to use a change of variables. I'm sure you can all understand why I don't want to use C as my hypotenuse, right? Because up to now, we've been using that for the speed of light. You know what I think is a cooler way to represent the Pythagorean theorem? And by the way, it's deeply connected to the study of relativity. Let's, instead of using A and B, let's call this leg the X coordinate. Let's call this leg the Y coordinate. And I'm going to use a very charged letter for the hypotenuse. I'm going to use S as the hypotenuse. So now our Pythagorean theorem would look like this. X squared plus y squared equals S squared. Now, if you're Vladimir and you're planning on studying mathematics in college next year, you might be curious as to why I chose the letter S, and I want to tell you. In special relativity, S represents what is called the metric. And the metric is a four-dimensional path through space-time. It's kind of like a hypotenuse that's not in 2D or even 3D. It's like a four-dimensional hypotenuse. And they call a path through space-time S. So in a way, by starting you off baby style, having you come to terms with S as a hypotenuse, I'm pre-gaming you for some much crazier stuff down the road. And we had to choose a letter anyway, so why not choose the real one, okay? All right, that's all you're going to need for this derivation. And you're also going to need to know the two postulates of special relativity. The laws of physics are the same in all inertial reference frames, and the speed of light is a constant for all observers. I also need you to know another thing, a thing that's kind of like common sense, but we should talk about it. And before we do any of this, I want to just come up with a key idea. Sometimes it is referred to as the relativity principle. And this isn't really about Einstein so much as just a basic concept from physics. And can I erase this here? Is everyone okay? All right. Let me write the idea down, and then let me see if you guys understand it, okay? So here's a key concept that we're going to need for this derivation. And the key concept, I believe it goes under the name of the relativity principle. And I want to state here, this is not a special relativity postulate. This was not invented by Einstein. It's a thing that you're kind of supposed to know from physics. And the relativity principle goes like this. An observer in an inertial reference frame can always argue that they are at rest, and basically it's everybody else are the ones that are moving. How can I say such a thing? An observer who travels in an inertial reference frame can always argue they are at rest and everyone else is moving. Clearly, if you were the dude on the skateboard at the beginning of our lecture today, would you not realize that you were on the skateboard and you were moving, you might ask? Allow me to construct a slightly different type of skateboard for you. What if I put you inside of a train, like one of those box cars that carries cattle? And I really greased up the tracks with butter and Crisco or something so that there was a very low degree of friction between the tracks and the wheels. What if I also covered the interior of the train car with high quality studio soundproofing foam? And then I made sure that there were no windows and that the velocity of the train car was extremely constant. Without being able to see the trees whiz by, here you are, you're going to sit on a chair inside this train car. The speed is constant. You can't hear any clickety-clack of the train moving outside. You don't feel any vibrations. You don't see any trees whizzing by. If you're that observer, even if you're traveling pretty fast, inside the car, it kind of feels like you're at rest, because there's nothing really to gauge your motion by. No auditory, no visual senses, no touch vibrations. In fact, I'd like to argue that it's actually impossible to perform any kind of experiment, physics, no matter how complicated, which might be able to prove that you were actually in motion. And one simple idea that I could have is to take Rainbow Ball and to just place Rainbow Ball here on the floor in front of you. And Rainbow Ball and you would sit perfectly still together. That would not be the case if the train car were to suddenly accelerate or to hit the brakes. The ball or the bag of groceries, as you know from driving your own cars, would suddenly slide forward and back, especially in my van where groceries go whipping all across the damn thing. In fact, this is a little bit of a diversion, but it's kind of fun. There's this kid, he won like a free scholarship to college and all of his tuition paid for and got money by making a little video in his mom's backyard about the postulates of special relativity. And this won him like $500,000 and a free ride to a fancy college. He didn't have any special tools. He just had a little crappy video camera. He actually talks about this relativity principle. And just because it's fun, kid wins relativity, one's scholarship relativity. Let's see if we can find this thing. I want to show you just 30 seconds of the video because it's cute. This will probably keep me from ever having revenue stream because I'm now showing another YouTube video, but I don't care about that. I just want to show you, I can't show you the whole thing because I don't have time for it. I just want to show you like the 30 seconds where he kind of explains the relativity principle. And I think he does like a pretty good job of it. Let's see if we can get it. Can you guys hear the sound here?
So Einstein said that the laws of physics are identical
try
in
this,
any
30 seconds.
inertial reference frame. One isn't speeding up or slowing down. But why does the speed have to be constant? Well, that's easy to prove. Just sit in a chair, grab a bowl of popcorn, place it in front of you, sit back, and watch how the laws of physics behave. Nothing's happening. Now let's do the same thing in a car with the windows blacked out. What if the driver decides to change the speed of the car drastically by stopping all of a sudden? All of a sudden, the laws of physics seem to act a bit differently.
All right, so anyways, that was like the whole video is kind of cute. They're very clever of him. And he's talking about the same stuff that we're learning about. This stuff is classic stuff. While we're on the subject of fun videos, I want to show you one more video, and this is especially for Vladimir's benefit here today. In the 80s, there was, you know, this during the height of the Cold War, there was this legendary 80s movie called Top Secret. And in the movie Top Secret, it takes place in East Germany. You kids are probably too young to remember this, but when I was a kid during the Cold War, half of the city of Berlin was occupied by the Soviet Union, and there was a Western Berlin where people were living in a Western society where they could have blue jeans and rock and roll and, you know, streak through naked through the neighborhoods or whatever. And then East Berlin was sort of Soviet occupied, and there were a lot of restrictions and rules on what kinds of media you could consume. In this hypothetical, basically shitty comedy movie, shitty 80s comedy movie, Val Kilmer plays an American rock star who gets a special permit to do a rock and roll show in East Germany. And so he's traveling there with his papers, and he's going to show these Stasis about, you know, rock and roll and apple pie and American culture, whatever. And the movie's totally ridiculous. But there's one moment in it that really sticks out here. It's a train gag. It's about 30 seconds long. And it's very interesting they put this in there because Einstein himself was from East Berlin. So they, I think, or maybe he grew up in Leipzig, but there's some connection there where they had to be thinking about this. And I want to show you this. Okay, so what happens in this 30-second video, if I remember the movie, I saw it when I was a kid. It's terrible, okay? But he gets on a train, and then the Germans are saying, "Show me your papers," and he's about to leave from the station. And I want you to just watch what happens.
If that was your idea of being an ambassador, we're headed for a lot of trouble.
Anyways, okay, so that's a terribly stupid movie, and you probably shouldn't watch it. But think about how perfect for our relativity lecture that was, where you see the train leaving the station, right? And you assume it's the train moving, but it turns out to be the station. This is the relativity principle in action. An observer in an inertial reference frame can successfully convince themselves that they're at rest. And it's the, I mean, after all, when the policeman pulls you over and says, do you realize that you were doing 80 miles an hour in a 30-mile-an-hour school zone? You don't reply to the policeman, 80 miles an hour with respect to what, sirrah? That would be a great way to get a taste of his brand new billy club right in your mouth. Okay, so you don't play those. It's assumed that everyone knows who is moving because you're moving relative to this epic inertial reference frame that cannot be questioned called the ground. Whereas we discussed before, the more you think about it, actually the ground doesn't actually constitute an inertial reference frame. Not only is it moving, but it's traveling in a circle subject to centrifugal forces. Oh, and by the way, Earth is traveling around the sun in a circle. Oh, and by the way, the sun is traveling around the galactic center in a circle. And by the way, the galaxies are all moving too. So in fact, there's nothing that's actually at rest. It's all effed up, right? Okay, with that in mind, who is moving and who is not moving is a very confusing idea. And if we were to go to outer space together, that would become increasingly more obvious. Without the ground as a reference point, there's only relative motion. There is no absolute motion. So can we agree on that? That idea is essential for what I'm about to do. So thank you for indulging me there. Okay, now we're going to set up the derivation. It's time for us to learn how time dilation comes about. We're going to set up an experiment almost identical to the one we began our class with. Okay, I've been grooming you this entire time. I'm going to create a train station just like the one that you saw in Top Secret. And on the train platform at the origin, I'm going to place an observer called A. I'm also going to use friendly, non-threatening colors to help you digest the mathematics better. A, the observer on the ground who is at rest, if you want to believe in such a thing. A, the observer at rest is going to be represented in green. And now I'm going to construct myself one of those boxcar trains that we talked about. I'm going to try to make this pretty consistent. So I'm going to make this train 20 centimeters tall and, oh, I don't know, let's make it 10, 20, let's make it 30 centimeters long. All right. And I'm going to show the train at two different positions during the course of the experiment. At the start of the experiment, observer B will be in a moving train car, and we're going to watch it roll forward in time at some constant velocity. A moment later, the train car will be over here. Let's give it a little distance. I'm going to try to draw it with the exact same dimensions. 30, 10, 20, 30 centimeters long and 20 centimeters tall. Okay, so follow along with me. I want you to draw all this stuff as part of your lab today, okay? That's the learning, is the copying and the watching, okay? Now, we're going to put observer B inside the train car moving at a very constant velocity. And to keep our theme of non-threatening colors, B's frame of reference will be represented by a blue marker, okay? And I'm going to perform what is probably the stupidest physics experiment ever conducted in the history of physics. I'm going to attach a red laser to the bottom of my cart, and I am going to fire this red laser from the bottom of the cart up to the top of the cart, where it will be received by a photon detector. The laser will travel the height of the cart, which we will define as capital H. That's the height of the cart. And the whole idea of the physics experiment is observer B throws the remote switch, fires the laser, it travels from the bottom of the cart up to the top of the cart, and observer B is going to measure the time that it takes the experiment to take place. I'm probably just going to, for the sake of convenience, have you pretend that the experiment takes 2 seconds from B's frame of reference, just because 2 is an easy, stupid number. In reality, the cart would have to be pretty damn tall for the photon to take 2 seconds. In fact, it would have to be 600,000 kilometers tall, would it not? Okay, so maybe it was 0.02 seconds, but who gives a shit? Let's just say 2 seconds, because 2 is easy, okay? Let's imagine that the cart rolls forward at a velocity that is constant. Now, in order for the effects of relativity to become obvious or apparent, this cart needs to be traveling like really fast. Maybe not the speed of light fast, but let's just say it's traveling at 80% the speed of light. When objects, and by the way, I want you guys to notice how I represent the velocity here. I'm drawing the velocity not in meters per second or in units of kilometers per second, but I'm representing it as a percentage or a fraction of the speed of light, 80% c. You will discover that most problems in relativity display the velocity as a percentage of the speed of light. The reasons why will become clear later, okay? One does not begin to notice relativistic effects, such as time dilation, until you approach roughly 20% the speed of light. Then shit starts to get buggy. Okay, pretend for a moment that you're observer A, and you're watching the cart roll forward quite rapidly in time. You guys agree that it takes time from the laser to go from the bottom of the cart to the top of the cart, right? And during that time, the cart is rolling forward, correct? So let's say this represents the start of the experiment, and this is the position of cart at the end of the experiment. B will start off here, and by the time the experiment ends, observer B will have rolled forward some distance in time. The laser will be roughly the same distance from the side of the cart. The detector is up here. Weirdly, if you're observer A, the laser beam does not travel vertically from the bottom to the top of the cart. And here's the trick, guys. If you're now, how could A watch the experiment but B not see the outside? Have you ever been to Stop and Shop and seen one of those one-way shoplifting mirrors? For the sake of argument, imagine that I installed a one-way mirror backwards on the train. A can observe into the train, but B cannot observe out. All right, just in case you're worried about that issue, I've got an answer for everything. Okay, according to observer A, as the cart rolls forward in time, the path of the laser beam will actually be a diagonal traveling from here when the laser is fired and carried forward in time to when the photons are captured by the counter at the end. I want to pause here and make sure you guys are with me because it's easy to get lost at any step of this process. Does that kind of thing make sense to you? That A will see it travel along a hypotenuse. Tegan, Mateus, Mariah, you all agree, right? Because the laser is being carried forward with the cart. It has to fire there. It has to end there. So it's now, I ask you something. Is the distance traveled by the laser according to B the same as the distance of the laser according to A? No. You can see that A will see the laser traveling a greater distance than B. But now I want you to think about things for a second. According to Einstein, both observers need to measure the same speed of light, no matter effing what, right? If distance equals rate times time, and both observers need to measure the same rate of c for the laser, if observer A and observer B measure two different distances, this implies that observer A and B instead have to measure two different times for the experiment to take place. Therefore, there is no longer a flow of time that is communal to A and B, but B has his own rate of time and A has its own rate of time. And the implication is that time is going to run at a different rate inside the moving train car. Woo-wee. What is our goal today? Our goal is, could we construct a formula that will express A's flow of time in relationship to B's flow of time, all dependent on how fast the car moves? And it turns out that's way easier to do if you than you might think. Okay, watch this. I'm going to construct myself a big old damned right triangle. This side of the right triangle is called H. It's the height of the car. This length of the triangle, from the laser beam at the start to the laser beam at the end of the experiment, I'm going to call this distance L. L represents the distance that the train car has rolled forward during the experiment from start to end. And then do you see this hypotenuse here? The path of the laser according to A? Because I need another letter, I'm going to call that S. Remember that S is my descriptor of a hypotenuse in relativity. Let's construct our Pythagorean theorem together, and you probably already know what it is. S squared equals L squared plus H squared. Are y'all comfortable with that? Did that make good sense? All right. By the way, if you don't give a shit, that's fine. But if you do give a shit, feel free to stop me if you get lost at any point, and I should be able to get you back on track, shall we say. Okay. Now what we're going to do is these are all distances or lengths. The height of the car is a length. The hypotenuse of the laser is a length. This is a length. Let's try to express them in terms of time using distance equals rate times time. Okay? So here's what we're going to do. Let's take an obvious one. The height of the cart. Would you guys all agree that the height of the cart is the distance traveled by the laser according to observer B? So the speed of light, according to Einstein, should be c. That's the velocity. But the time should be b's time, because b is watching the laser travel h from the bottom to the top. So this is distance equals rate times time for the laser beam according to b. You comfortable with that? All right. Now let's deal with S, this big long hypotenuse. S is the path of the laser that A sees, correct? So A needs to also measure the same velocity for the speed of light, that's c. However, the time is now not going to be B's time, but it is A that observes the laser travel along the hypotenuse. This becomes T sub A, which we do not expect to be the same as T sub B. Did that make sense?
Yeah.
I need one more distance equals rate times time. Let's deal with the L, okay? L is the distance the cart travels. So this is not a laser beam anymore. This is the train car rolling forward. L will be the velocity of the cart times a time, but whose time shall we use?
Yeah, like who's the observer?
Well, this, if you're following me, if you're paying close attention, you should be able to deduce it, but I want to see if you guys are good. L is the length of the car, V is the velocity of the cart, but whose time should be used here for the distance traveled by the cart? Whose time? There's not one time anymore. There are multiple times.
Ace, because B is stationary.
More importantly, Vladimir, B is in an inertial reference frame where B is not actually aware that B is traveling because we
that too.
Windows. The only observer in this experiment who is conscious of the roll of the cart is A, correct? According to B, he might as well be sitting in the train station. There's no difference to him, correct?
I forgot that he doesn't know. Well, they.
That person. But in any case, Vladimir, whatever your logic was, you had the right answer. This is distinctly A's time, and I want to make sure you're comfortable with that, okay? Okay, let's plug this and this and this into our equation, and let's do a little backyard algebra, which I might be able to speed up for you. Okay?
Backyard algebra.
Um,
So does S have to be a line?
yes. What else would it be?
I mean, you said it's symmetric through 4D space-time, so it's like, does it have to be a line?
Actually, yes. There is another rule in relativity. You're not going to like the sound of this.
Oh.
A photon must always travel along a null metric in four-dimensional space-time. What the F does that mean? It means that photons always take the shortest path through space-time.
It's always a straight line.
Well, it's
Oh, wait,
not a
no?
straight line in 3D space, but it's
Okay.
a straight line in 4D space. Sorry. You know what? Don't ask too many questions, Vladimir. You're going to get spooky answers, okay? All right, listen.
Wait, is it about the shape of the universe?
Yes, and we have to wait for general relativity until we can talk about it.
Damn
Vladimir,
it.
your
Okay.
questions are good, and they will be
Okay.
addressed at the
All right, I'll
appropriate-
shut up.
No, I want you to, this is a dialogue, okay? I need to do some algebra, and I hate to erase this beautiful drawing, but can I do that? Do you guys have this? All right.
I mean, I don't have as many colors as you do. I kind of just have a blue and the gray of my pencil, so.
I accept. All right. Let's do a little time dilation algebra. I might need your help remembering all this stuff. So we had S squared equals L squared plus H squared. And now what I'm going to do as quickly as I can with as many colors as I can, I'm going to substitute all of those distance equals rate times time equations in there. And I'm going to distribute my square, unlike my college student friends who forget to do these things. Watch my moves here. In for S, I'm going to put the speed of light times A's time, and all of that is to be squared. In for L, I put the velocity of the cart times A's time. Once again, all of that is to be squared, plus H, which is the speed of light times B's time. All of that is to be squared. Now, I distribute my squares, and I shouldn't have to make this a step, but I know better with you guys. I'm going to actually make this a step, because y'all forget to distribute your squares, and it's deeply upsetting to me. Okay, TA plus C squared TB squared. All right, so all I did was distribute the squares. Now, in a weird, fucked up way, we're kind of already done with our equation. We have an expression which expresses B's time in terms of A's time, and the only other numbers left in the game are the speed of light, which we know already, and V, the velocity of the cart. In other words, the velocity of the cart determines the difference between the rate of time in A's frame versus B's frame. However, we would like to clean this up with algebra, and I would like to end up with an expression where I have TA on one side and TB on the other. That way I can say if an experiment takes this long in B's frame, how long does it take in A's frame? Do you follow me? So for that, we're going to have to do some algebra. It turns out the smartest thing to do first is to divide all terms in the equation, sorry I didn't use red, by C squared. And if you do that, it knocks out the C squared there and there, and it kind of plugs the two velocities together. So let me write this again. My algebra is going to go faster than you guys would like, but that's because our time is limited, and you guys get bored quick, and we can't have that, okay?
Wait,
So
but
I'm
isn't
actually, oh yeah, Vladimir?
But isn't the velocity of the card it can be expressed in C?
That's my plan, bro.
Oh, okay.
You and I are talking the same thing, because watch. I'm trying to get the velocity of the cart and the speed of light together just for that reason. So in this term, I will have the velocity of the cart as a fraction of the speed of light. Now it should be v squared over c squared, but I'm going to pull some sleight of hand shit. I'm going to factor out the square times ta squared plus tb squared. And now what I'm going to do is, remembering that there is always a magical 1 in front of every term. My friend at CCRI, my mathematics professor friend, calls this clever forms of 1. You can always put a 1 out in front. I'm going to take this term and I'm going to subtract it from the other side and factor out the ta squared. You're not going to like that. All right. So 1 minus v over c. I actually did two things at once here, so make sure you can handle that. 1 minus v over c squared times ta squared is equal to tb squared. Did that make sense? Or did I jump too many stones ahead for you? I subtracted this term from that side, but since it had ta in both terms, I yoinked it right out of the parentheses. Okay? Now, I'm going to take this yucky little blob, 1 minus v over c. Wait, sorry. Oops. This sucks, but I'm going to have to use hard brackets. Okay? Can you guys modify that? That's how it's supposed to be. I'm going to take this nasty little term, 1 minus v over c squared. I'm going to divide it by the other side, which is customary. And I'm going to write ta squared is equal to tb squared divided by 1 minus v over c squared. And we're basically done. One does not prefer to work when squared time. One prefers to work in regular time measured in seconds. I'm now going to square root both sides. Hey, does everyone have this bottom line? I got a better idea. Algebra, algebra, algebra. Okay. And finally, at the end of all of the algebra, we arrive at our final expression for time dilation. Ta, the rate of time measured by observer A, is Tb, the rate of time measured by observer B, divided by this crazy special relativity whack factor, which is the square root of 1 minus v over c squared. The first time I learned the equation for time dilation, it was presented to me like this, and I thought, what the F-U-C-K? How did Albert Einstein figure out radical 1 over v minus c squared? That blew my mind. This is the equation known as time dilation. And what it means for people who have ears or people who can understand math, it means moving clocks run slow. If you can figure out who's moving, that is.
I have a question. Why does the square root go to the bottom of it instead of the whole thing?
Great question. One of the rules from mathematics is, just as you have to distribute a square, you must also distribute a square root, Mateus.
Okay, I got it, because the other one, it's canceled. Yeah.
Radical x over y is equivalent to radical x over radical y. My goal was to get rid of the squares, so I had to square root all damn sides of the equation, which ends up square rooting this. The square root of the square kill each other off, which was the goal. But then basically I put all of the nastiness down here so I could just have the times by themselves.
Thank you.
Cool. All right. For you to really understand the mind fuckery of this whole thing, I need you guys to do a sample stupid problem with me It also would be a great idea for me to show you how to punch this because there's lots of places to make mistakes. Let's go back to the beginning of my rolling cart experiment where TB, observer B, measures 2 seconds for the laser to go from the bottom of the cart to the top of the cart. The question we want to answer is, how long does the experiment, but here's where I'm going to introduce a fancy vocab term. How long does the event, an event is a charged word in relativity. How long does the event take according to A? The answer is use time dilation. Okay, first I want to convince you that V divided by C is equal to the following thing. Do you remember what the velocity of the cart was?
80% C.
Watch me substitute in for V 80% C divided by C. So it's 80% the speed of light divided by the speed of light. In other words, V over C is just 80%. And here I'm going to write vibe check. That's the whole idea, is that whenever you see V over C, you just simply plug in the percentage of the speed of light. Okay? That's the trick. All right. Now we're ready to set up our equation. Follow along with me. I might just drop the colors for a second. Well, I'll keep red for the speed of light, but I'll speed this up if I can drop some of the colors. TA will measure a time of 2 seconds divided by the square root of 1 minus 0.8 squared. You all agree with that? Because V over C is 80%, right? Okay. Calculators out. I'm not even going to let you try this one on your own, okay? You're going to follow me. You're going to do this in memory of me. Okay, let me explain the concept before we punch it. What we're going to do is we're going to plug in this stuff first, and we're going to hit equals. Then we're going to take the square root. Then we're going to reciprocal it. We're going to take the reciprocal to flip it to the bottom, and then we will times it by 2. So
Wait,
let's
can
do
you,
that.
so
Huh?
can I check it? Can I check if I did it correctly?
What'd you get?
All right, don't punch me. 15.43.
Nope, you screwed it up.
Okay,
You forgot to do something at the end.
well,
Okay,
can't blame you for trying.
sure. Can we do it my way now?
Yeah, sure, absolutely.
Okay. Let's do 1 minus 0.8 squared, and then I want you to hit equals. Do you all see this? Okay. Now let's square root it. Shift, square root. So far, so good? Now we're going to take the reciprocal so we can, because we basically did all this, we have to flip it to the bottom. Shift, and the reciprocal key is close parentheses, 1 over x. Is that what you got?
Yeah.
Times 2 seconds equals. This should be our final answer.
So even at 80% speed of light, the event lasts only like 1 more second.
Okay, that's one way to look at it. Here's another way to look at it, Vladimir. TA and TB are times, and whatever units you use for A have to be the units of TB, correct? So I use seconds here, which are MKS, but this experiment would kind of run the same. Suppose the laser beam, according to B, suppose the event took 2 years. At 80% the speed of light, let's say you bounce the laser back and forth 50 bazillion, trillion, gazillion times, okay? So many times that the laser beam took 2 years to complete the experiment. How many years would the experiment take relative to A? Who's talking right now? Is that you, Vladimir?
Oh, hold up. I forgot to mute myself.
It's okay. Vladimir's mumbling to himself. So the question I asked is, what if the experiment took 2 years relative to B? How long would it take according to A?
Uh, 3.3 years.
Right. So you say, oh, Brendan, it's only 1.3 seconds difference, but that's 1.3 seconds out of 2 seconds, which is a 33% increase or more. If it was 2 years, you'd get a whole extra year and a third, right?
So it's about the percentage.
Yeah, that's a big flow. Oh, by the way, let's go back to 2 seconds again. Whose clock ran slow? A's clock or B's clock? What time is the slow time? A or B?
The B's clock.
Why is, people might actually have to think about this. Why is 2 seconds slower than 3 seconds?
Well, it's like while you ran 300 meters, I ran only 200 meters. So you ran faster.
Yeah, it's about the flow of time itself. So let me draw 2 clocks so that you can understand this. On the left, I will draw B's clock. On the right, I will draw A's clock. Let's make some tick marks, right? 0, 1, 2, 3. For B's clock, the hand on the clock ran 2 seconds, right? Whereas for A's clock, the hand on the clock ran more like 3 seconds. So for the same event, the rate that the needle is twisting is slower in B's frame than it is in A's frame. Pretty weird, right? Moving clocks, the B clock, time is running slower. By the way, suppose you were observer B and you were inside this so-called slow frame. Would it feel like time is running slow? No. In your frame, you would consider the passage of time to be normal. But if you looked out that window back at A's time, well, his time would be all kinds of fucked up, right? In fact, here's where things get really, really messy. We've already seen that time flows at a different rate for observer B than it does for observer A. And I mean all of time. It's not just like the tick of that laser. Everything happening with inside B's frame, right down to the rate of his heartbeat, is different for observer B than it is for observer A. This has been confirmed experimentally kabillions of times. Now I'm going to ask you a really confusing question that really gets at the heart of what relativity is all about, okay? Do you have all this? How am I doing on time? I'm almost out of time, so I want to get to the real conundrum here, okay? Okay. Observer A is on the platform. Observer B is inside the train car. And observer B is firing the laser from bottom to the top of the car. we've so far learned that the time according to B is 2 seconds for the event, for the laser beam to fire, but that if A holds a stopwatch, the time according to A for the event to take place is 3 seconds. And we decided that the moving clock and we defined moving as the train car rolling forward at 80% the speed of light, that the moving clock ran slower than the rest clock, the clock at rest, correct?
Yeah.
What if we now ask a more awkward question? Suppose B drills a little hole into the side of his train car, and he takes out a telescope and he looks out at A's reference frame and he observes the rate of time flowing in A's clock. Do we all agree that B constitutes an inertial reference frame? Yes or no?
Yes.
Because his velocity is constant. Do we also agree on the relativity principle, the top secret train gag, that all observers moving at a constant velocity could successfully argue that they are at rest and all other observers are moving?
Oh, I see what you're getting at.
All right, now wait a minute. B, as nutty as this sounds, could easily argue that the train station and the entire Earth beneath him are actually traveling at a velocity of 80% the speed of light, while he himself remains at rest. Okay, let's say you truly understood what I just said. Here's my next question. How much time has elapsed in A's frame according to B, who measures 2 seconds? I dare one of you to tell me the answer.
1.3.
Holy shit, you're good. You are really, really good. I did not expect you to get that. Wait, not 1.3.
Ah,
I thought you were good.
too bad.
Well, you're just not good enough, that's all. You're not good enough, Vladimir.
Okay, let's try again.
What an inspiring teacher I am.
For real.
I think you
Okay.
guys are, look, it's not your fault. This is a confusing as fuck question. We need to walk through this slowly and carefully. Okay, here's the concept. Up to now.
Actually, wait, we can use the same formula.
Yeah, but how do you use it? That's the, of course you got to use the same formula, but how do you use it?
Because I tried to do without it, so now I just realized it was a big mistake to not.
Can I
So
just, look, time is precious and people have stuff.
Okay, my bad. Yeah, of course. Yeah.
Let's just have me walk you through this real quick, okay? Up to now, our whole derivation has been predicated on the concept that A is the observer at rest and B is the observer traveling, right, in a moving car. Now we have B considering their self to be at rest and A to be moving away from them. In a sense, this reverses the positions of A and B in the equation. B becomes the observer on the platform and A becomes the observer in the train car. This version now looks like TB is equal to TA times the square root of 1 over point A squared. And we already decided that TB, which is now the observer's time, is 2 seconds. Since this term here boils down to basically 60%, if you do the radical 1 over 1 minus 0.8 squared, TB, the time that B observes for A, okay, things get a little messy here when we talk about TB and TA. The time that B observes for A, which this is TB measuring A's frame. It's not exactly A's time, it's B's observation of A's time. Okay, Mateus, that's fine. I'm glad you're here. I get you. That's a good strategy. B's observation of A's time is 2 seconds times 60%, or 1.2 seconds. In other words, put this in your pipe and smoke it. There are now 3 times for 2 observers. There's the time that B thinks the experiment takes, 2 seconds. And I shouldn't say thinks, because it's not perception, it's measurement. B measures 2 seconds for the laser beam to fire. A measures 3.3 seconds for the laser beam to fire. But B believes that A is moving and that his clock has only shown 1.2 seconds of elapsed time. Each observer sees the other observer's frame as moving slower than their own. 3 times for 2 observers.
So the more observers we have, the more time dilation?
Or the more fucked up times there are. But the amount of dilation depends only upon one thing, the relative velocities. Okay? Exactly. That's the whole point. In fact, can I tell you something? We travel at speeds on Earth much slower than the speed of light, which is why even if I travel to school at 90 miles an hour in my van, we don't notice much time dilation at work. At speeds that are achievable in a high-speed commercial jet, you're still traveling much slower than the speed of light, but you can measure time dilation effects out to like 1 part in a billion precision, just small variations in time. In the 1960s, 2 famous physicists named Halfili and Keating got funding for a high-precision atomic clock, some kind of a cesium atomic clock. And they took 2 atomic clocks, they left one on the tarmac at an airport in like Washington, D.C. They put the other atomic clock on a jumbo jet, and they flew it around the world like 2 or 3 times. When the jumbo jet lands on the tarmac, the 2 clocks had showed a different rate of time that was exactly the same calculated by the time dilation formula. In other words, this shit ain't fake. This shit is real. You just ain't never noticed it before. In fact, there's a legendary picture of the Halfili-Keating experiment, and you really have to take your mind back to the 1960s here, that kind of Mad Men era. And this will be the last point I make before we stop. But if you look up this in the internet, Halfili-Keating experiment, there's a legendary picture from Life magazine where they did an article about it. And unfortunately, the only picture that survives, the one that I like, is super, super low resolution. But I'm going to show it to you anyways, because it's just so classic. Okay, so what we see in the picture is we see the physicist have Feely and Keating, all dressed up in their Mad Men era 1960s suits, sitting there with the two atomic clocks in the airliner. And here's the stewardess who's probably serving them highballs and martinis during the whole experiment. And they all decide to take a picture for posterity. And the two scientists are sitting looking serious. And the stewardess is sitting there kind of casually glancing at her wristwatch, which is a total double entendre joke, where she's saying, okay, yeah, we're doing an experiment with these two physicists on time, but also like, look at the time, like this is really fucking boring, right? So it's kind of a beautiful little joke that the three of them are in on together to show you that you can do science and be a nerd, but you can also have fun and drink whiskey while you do it, okay? So that's the moral of today's story. Time runs at different rates, and it's always good to get complimentary drinks on your airline when possible. So this is going to lead to a much more bizarre conundrum called the twin paradox. And there are other consequences of special relativity besides time dilation, but we're out of time for today, so we'll cover those on Thursday. Now, what are you going to turn in? Everything we did to derive the time dilation formula. So just whatever couple of pages of notes you had. Can you do that for me? Okay.
Yeah.
And all you
So
viewers,
all 3 times are correct?
they are. In fact, that's a question that people ask. Which time is the correct time? In fact, Vladimir, on that note, I want you to add one more time to this. The truth about, or not one more time, but one more note, okay? Because A and B's position can easily get reversed, and because we can get confused about who is in motion, the proper way to write the time dilation formula is in this fashion. Rather than using A and B, we say that the observer time is the rest time divided by 1 minus the percentage of the speed of light squared. T here represents the observer, who's usually the scientist or the astronomer on Earth. We call this time the observer time. That's the one that you want to calculate. We call this time the rest time. But if you think about it, who is actually moving and who is at rest depends somewhat on your reference frame. Each observer can argue that they're at rest successfully. Each observer can argue the other one is moving. So here's how we define the rest time. Do you all agree that we started off by measuring the laser beam? That's what we were timing, correct? The laser beam was the event. In whose frame is the laser beam located?
B's frame.
In B's frame. Therefore, B is the rest time. It's not that B's at rest. He's clearly in a boxcar. It's that B is at rest with respect to the event. The event is the doodah that you are measuring, whether it's a supernova or a pulsar, or in this case, a laser beam. And that's the last note that I wanted you to take. I want you to take this note. The rest frame is the reference frame in which, and here I'm going to use that loaded term again, the event takes place. And if you can understand that statement, then you've gone a long way to understanding the weirdness that is special relativity. Thanks for that question, Vladimir. I actually wanted to include that in our lesson today. That was a sort of a key concept, all right? The rest frame, put that in parentheses because that's a term people use. The rest frame or the rest time is the frame in which the event takes place. The event in this case, of course, just so that it's obvious, The event is the laser. But it's not always going to be the laser. All right. Congratulations. You've learned a little bit about relativity. You're going to learn a lot more, and you're going to learn about general relativity, which is even crazier, on Thursday.
I always thought that since special relativity is special, it's harder.
Actually, special relativity is the simpler case. That's where you have constant velocities. Albert Einstein then proceeded to spend another 10 years trying to derive the theory for when you had accelerations included, and he accidentally stumbled on a new theory of gravity. What's so freaking cool about Einstein is he set out to do this really hard thing. It took him 10 years, but he actually did it, and he derived the way more insanely complicated general relativity.
It wasn't like some sad story about work in vain where you didn't actually achieve anything at the end.
No, that's another famous physicist named Gaunt, I believe. But that's a story for a different day. Okay. Like, comment, subscribe, and all that jazz. Turn in your labs. Please turn them into Lab 10. Do not be confused. I'll see you guys on Thursday where we're going to do our special relativity homework from chapter S2 and S3. Okay? Okay, guys. Have a great day. Enjoy some sunshine. Peace out.